Hi everyone, so this is a review for Chapter 13 Revision Quiz, Set 2. So based on the responses that we received, I think we'll be discussing question 3, 4, 5, 11, and 15. A total of 5 questions. So let's look at the first question. Question 3. The temperature of 2 moles of diatomic gas. Okay, so a lot of information suddenly. 2 moles of diatomic gas is raised by 8 degrees Celsius from the room temperature. Okay, so let's write down what we know first. The temperature is 2 mole. That is a diatomic gas. So if you know it's a diatomic gas and they didn't really specify, they specify room temperature. So room temperature is not high. So if you see the word diatomic gas and the temperature is not extremely high, you will know that the degree of freedom will be 5. Okay, this 5 comes for 3 comes from translational, the 2 come from the 2 rotational axis. So you have 2 omega and 3v. Vx, Vy, Vz, then omega x and y probably. Okay, so that's diatomic gas and it's raised by 8 degrees Celsius. So you know that the change in temperature is equals to 8 degrees Celsius because change 1 degree Celsius increment is the same as 1 Kelvin increment. So 8 degrees Celsius is also the same as 8 Kelvin. There's no conversion, okay? 1 degree Celsius is equals to 1 Kelvin. So if you increase by 8 degrees Celsius, means by increase by 8 Kelvin. Okay, no difference. So it's from room temperature, therefore there's only 5 degrees of freedom. So now they ask the increase in internal energy of the gas is, so they now ask for increase in internal energy, means by they are finding change of U. What is it? Okay, so change of U, you might immediately think of chapter 14, change of U equals to K minus W, not K, Q minus W, but that's not what we are looking for. You need to know that U is equals to F over 2 nRT. So this is the internal energy that we have. So F will represent the number of degree of freedom, N here represent the number of mole, R2 represents molar gas constant, T represents the temperature. So with this case here, we can build this thing. Change of U is equals to UF minus UI. So if we don't experience any change in degree of freedom, the degree of freedom we don't need to put initial final. There's no change in the number of diatomic gas. So the N will remain the same, so you don't need to write N2 or N1. There's no need for it. R is always a constant. The only thing that changed probably is the temperature. Yes, they say the temperature is being raised. So it means by you have final, then you minus, then you have the same thing, but your temperature will be T initial. So if that's it, that means by, if I do a bit of factorization, that will be Tf minus Ti. And Tf minus Ti is just change of temperature. So it's delta T. So this is the temperature that we are going to be using. So we want to find delta U and it's equals to 5. Our F is 5 over 2. And R delta T. Okay, let's just write down first. Okay, as usual, keep it a practice. Always start with formula first. Then substitution. 5 over 2. Number of mole is 2. Gas constant 8.3145. Change in temperature is 8 Kelvin. So once you write down all these things here and you do some calculation, the answer that you get will be 332.58 joule. So 332.58 joule, if you do it, change it into standard form, then it will be 3.32 times 10 to the power of 3 joule. So from here, we can get our answer to be C. Okay, so it's a matter of calculation. If you're being patient enough, I think this question should be doable. Okay, so that's all for question 3. Let's look at the next question. Question 4. The air inside a hot air balloon is heated up from a density. So this is the initial state. The initial density is 1.25 kg per meter cube. From a density means by initially it has a density of 1.25 kg per meter and a temperature of 27 degrees Celsius. This is the initial temperature. Okay, it's heated up from this initial state until the balloon starts to float or begins to float. Okay, so until the balloon begins to float, probably that's the final situation. We're not sure, but let's see. Okay, so during the heating process, some air escapes from the balloon. When they say some air escapes from balloon, what you should be aware of is the N1 is no longer equals to N2 because there's gas coming out from the hot air balloon. Okay, then the pressure inside the balloon remains constant. So that means by the initial pressure and the final pressure should be the same. At just above the atmospheric pressure. Yes, you have to be slightly above the atmospheric pressure. The mass and volume of the air in the balloon just before it rises is 300 kg and 400 meter cube respectively. So this is just before it rises. So this just before it rises is actually the final state. Okay, because it say until the balloon, here it say until the balloons begin to float. So begins to float too is like final is our final situation. So you see, just before it rises, so means by we are reaching our final state. So our final state, they tell us that you have a mass of 300 kg and the volume of 400 meter cube respectively. So they ask for the temperature of the hot air. So let's just list down everything that we know. We know that the number of mole will not be the same because there's air escape from a balloon. And we know the pressure remains constant, so P1 equals to P2. Let's just write down everything. Before that, you know our density, initial density, rho 1 is equals to 1.25 kg per meter cube. Then the initial temperature, T1 is 27 degrees Celsius, which if you do a bit of conversion, 273.15 plus 27, that will be in terms of Kelvin. So if you calculate everything, it will be 300.15 K. So these are the initial things that we know. How about the final? The final, they say the mass of the balloon, so mass of the air in the balloon. So let's just write this as big M, because big M is usually for bigger cases. Then we write total because it's not molar mass. If molar mass, then it's a capital M. But since it's all the air in the balloon, let's just write M total. Then it's equals to 300 kg. And the volume of the air, big V, is equals to 400 meter cube. Be careful, these are final states, so label it as 2. Okay, so these are all the information that you know. Now they ask for the temperature of the hot air. If they ask for temperature hot air, what you can do is you can think of it like a ratio question. So if you think of it like a ratio question, first thing is find what to express. So if what kind of relationship you want to express, you are finding the temperature of hot air. So probably you can find the temperature final over the temperature initial equals to what first. And then since you know T1 is equals to 300.15 K, you can just substitute in this later to get your T2. You can treat it like a comparison question first. So if you know what to express already, then the next thing is relate to what you know. Okay, you relate to what? You relate to what is given in the question. Things given in the question, they give you density, so you know you need to somehow deal with density. Then there's temperature involved. Okay, so what can we do here? What kind of things can we do? So PV is equals to NKBT. Probably we start from here. If you have a difficulty to think where to start, right, you see that pressure is constant and they give you something about temperature. So if you relate pressure and temperature, the best bet that you can do is PV equals to NKBT or PV equals to nRT. Now, I think if you use any of them, it should be fine, okay? nRT should be fine, NKBT should be fine as well. So you want to change it to be T as a subject. At the same time, you want to include rho, our density, inside this equation. So how do you make rho? How to put in rho is you have to try to relate things to rho. So what I think is, okay, this one is also a quite difficult question for me. So it takes some time for me to figure out how to do it. So first I shift it like this. Then I see N over V is the total number of molecules divided by the volume. So what you get here is actually the number density. Okay, means by how many gas molecules there are per unit volume. We call it number density. How many gas molecules there are per unit volume. Okay, so once we reach this state, we know that for each unit volume, there will be this much. For each unit volume, there will be this much gas particles. So if we know how much mass does each gas particle has, then if you take the mass of one gas particle, multiply by the density, then you know the mass per unit volume, which is just density. Okay, let me write it down something, then probably you'll be able to think of it better. So it will be equals to NV times M times 1 over M kVT. Okay, M times 1 over M is just 1. So what I do is I create a M over M, then I split it open. Because I want to combine NV, N over V times M here to become rho, to become density. How is this thing become density? Again, number density is number of gas particles per unit volume. So if you multiply by the mass of one particle, then you get mass per unit volume. N here times M represents the total mass of gas. N here multiplied by M represents the mass of gas in total. And you divide it by V, then you get the mass per unit volume. Mass per unit volume is just density. Okay, so density multiplied by 1 over M kBT. So if you rearrange a bit, okay, let me write down this P here. Okay, to rearrange T as our subject. If you rearrange T as our subject, what can we do? We do a bit of shuffling. Then become MP over rho kb. Okay, I shift the M from down to up, then rho and kb go down. So this is our expression. And now we know this is the expression, and we can relate T2 and T1. So we are finished with step number 2. So we move on to step number 3. Okay, step number 3 is to do your algebra. So we start with what we have said in part 1, T2 over T1. Then we write down M1 P1 rho 1 kb. Kb is a constant, so no need for 1. Oh, this is not 1, this is 2. I'm confused. Okay, M2 P2 over rho 2 kb. Then you have M1 P1 over rho 1 kb. Okay, so what can you do here? M2 is the mass of one single gas molecule. M is the M over here, right? Okay, so M here represents the mass of one molecule. So now if I ask you whether the molecule initial mass and the molecule final mass, are they the same? Yes, they are the same because it's the same air. You don't change the air. So if before that you have this molecule, after that you have the same molecule, so the same molecule should have the same mass, right? So you can say M1 is equals to M2. Okay, then the next thing you can also say is P1 is equals to P2, because they say here in the question, pressure inside the balloon remains constant. And I write here P1 is equals to P2 already. So that's one more thing that we know. So what can we do now? With that, we can do a lot of stuff already because things can cancel out. M2 and M1 can cancel out because they are the same. P2 and P1 can cancel out because they are the same. KB is just a constant and you can cancel it out. So now if you want to rearrange this equation, it will be 1 over rho 2 times rho 1 over 1. So it will be equals to rho 1 over rho 2. So rho 1 is the initial density, which is here, 1.25 kg per meter cube. So rho 2, how are you able to find rho 2? So here's something that you need to relate. If you look here in this part, you see that the total mass is given and the volume of the container final is given. So if the total mass is given and the volume is given, well, we need to recall some secondary school knowledge. To get density, you take the mass divided by the volume. So that will be 300 divided by 400. So with all those things plugged in, we were able to find that the answer is 1.666 T1 equals to T2. So now it's a matter of substituting things inside. So we substitute, where's our T1? Our T1 from here, 300.15 K. So if we substitute 300.15 K, and our answer will be 500.25 Kelvin. So, well, is there any 500.25? Let's look at our answers here. Well, there's one. There's a 500 which is very close. Okay, usually if you're doing this chapter's question, the answer will slightly deviate between your answer and the option. Why? Because some people take 273.15 when they are changing it to Kelvin. Some take 273, some take 273.2. It depends. And if you are using R, then R, some people use 8.31, some people use 8.3. I myself use 8.3145. So it depends on people what constant they use. You get somehow slightly deviated answer. But the correct constant you should use is based on the constant sheet given in the exam. So if the constant sheet have 2 decimal places, you follow 2 decimal places. Always follow the constant sheet. Okay, so again, this is the way we do for ratio question. I solve it using the ratio idea just to solidify your understanding on how to solve ratio question. So that's it for question 4. Let's look at the next question. Question 5. A cylinder of volume 0.09 meter square contains an ideal gas at 100 degrees Celsius and 8 times 10 to the power of 4 Pascal. Well, that's plenty of information. First time we are given so much information. The volume 0.09 meter square. Temperature is 100 degrees Celsius. As usual, when you're dealing with physics, changing it to Kelvin is a better choice. There are some times that you don't need to convert, but just to be safe, just convert it. Then you don't need to confuse whether need to convert or not. So this will be 373.15 K. Then your pressure is 8 times 10 to the power of 4 Pascal. Okay. If the mass of 1 mole of gas is 0.034 kg, mass of 1 mole of gas, what does it mean? Well, you have to recall your chemistry, but mass of 1 mole of gas is just molar mass. So molar mass we usually represent it with capital M and it's equals to 0.034 kg. And now what they are asking for? They are asking for the RMS speed. Okay, let's label this mass is 0.034 1 mole. So now they ask for VRMS speed. So this should be a relatively direct question. VRMS speed, you know that there's 2 formulas that can relate it to temperature. It's either 3RT over big M, the molar version, or you can do the VRMS equals to 3 kBT over the mass of 1 molecule. So if you look at the situation here, they give you molar mass. So if you are hesitating which equation to choose, they are the same equation. But since they give you molar mass, picking this equation will be a better choice because it's in molar mass, it's not in mass per molecule already. So this will be more straightforward. So what can we do? It's just substitution, okay? This question should be quite direct. So 3, R will be 8.3145. Then temperature should be 373.15. Then the mass, the molar mass should be 0.034 kg. Then if you calculate everything, your answer will be 5.23 times 10 to the power of 2 meter per second. Then your answer will straight away be this. Okay, so it's a rather straightforward question. So I think if you pick this question as a question that you don't know, probably you are hesitating which equation to choose. But let me prove it to you that it's okay if you pick any equation as long as you know what does the symbol stand for. Why do I say so? Okay, so let's be careful and be aware that this M here is mass of one gas molecule. Okay, so are we able to find the mass of one gas molecule? Well, actually, you can. Molar mass is the mass of 6.02 times 10 to the power of 23 gas molecules. Molar mass, right, is the mass of 1 mole. So 1 mole, you have 6.02 times 10 to the power of 3, also known as Avogadro number. Okay, so this is molar mass. So if you want to find the mass of one single molecule, what you can do is just take this molar mass divide by the Avogadro number. So if you calculate it, oh, I didn't calculate it, I need to calculate it right now. So 6.02 times 10 to the power of 23. The answer that you will get is, before a while, your answer will be 5.65 times 10 to the power of negative 26 kg. So this is the mass of one molecule. So now you are able to use this equation, this alternative equation. So what you do is just substitution, the same substitution. So 3, Boltzmann constant is 1.38 times 10 to the power of negative 23. Temperature, the same temperature, 373.15. And the mass of one single molecule, copy what I've calculated just now, 5.65 times 10 to the power of negative 26. So if you calculate everything, okay, let me check it to be very, very sure. If you calculate everything, the answer should be the same. Yep, it's also 522.89 meter per second, which if you change it to standard form, it will be 5.23 times 10 to the power of 2 meter per second. So as you see, you are able to get the same answer as long as you know what are the equation, what are the symbols, what you need to sub inside. Okay, so that's it for question 5. Let's move on to the next question. Okay, so this is question 11. For question 11, you are asked, they give you the speed of 8 particles. Okay, be very careful. The number of particles given is 8. And they are distributed in the table above. So this is a table, I crop it out. So what the table says here is you have one particle which is moving with 1.0 meter per second. You have one particle moving with speed of 2.0 meter per second. Two particles are moving with 3.0 meter per second, and so on. So now they ask for the root mean square. If they ask for the root mean square speed, again, you need to recall what is root mean square. VRMS, remember, is you square something, then you get an average of it, then you square root the answer. Okay, so here, what I have here in this picture is V, right? So what I need to do is I need to get V square for everything. So I need to get V square. This one will be 1.0, 4.0, 9.0, 16.0, 25.0, 36.0. So it's just you take the value of V, you square it, then you become V square. Okay, quite direct for now. So once you get V square, the next step is you find an average. So average means by you sum up everything, then divide by the number of things. So now there are 8 particles, so means by you need to sum up 8 things. So to sum up 8 things, you have to count, there must be 8 things. So there's 1.0 one time, there's 4.0 so once, but there's 3.0 meter per second. So means by you need to add 9.0 2 times, because there's 2 particles moving with speed of 9.0, and there's 1 particle. It's not speed of 9.0, it's speed square of 9.0. Okay, and there's 1 particle moving with speed of 4 meter per second, so you have V square of 16.0. Then you have 1 particle moving with V square of 25.0, and you have 2 particles moving with V square of 36. 2 particles moving with V square of 36. So you have 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 particles. So that's what they mentioned in the question. So what you need to do now is get average total number of particles, 8. So what we have done here is we have completed the inside of the square root. You are finding the average of the square right now. So the last thing to do will be close out the bracket, close out the square root. So what we do is we close out this square root. Okay. So if you calculate everything, I believe the answer you should get is 4.12 meter per second. And 4.12, that's a suitable answer, which is 4.1. Okay, so it's a relatively direct question if you understand the meaning of root mean speed. Root means square speed. Okay, so that's all for question 11. Let's move on to the next question. The next question says the VRMS speed, the RMS speed of a gas molecule is square triangle bracket V when the temperature is 350 K. So let's just write it down. VRMS at situation 1 is equals to triangular bracket of V. And at this moment, the temperature 1 is equals to 350 K. Now what they're asking for is what is its value at the temperature of 525 K. Well, the question is not very nice in terms of wording, because its value, what do you mean by its value? Okay, so here you have to do a bit of smart guess. So they give you temperature value, final temperature, and its value. So if they use its, means by this thing is being mentioned in the earlier sentence. So if it's being mentioned in the earlier sentence, you can probably deduce that the only thing left is RMS speed. So they are asking for the final RMS speed actually. So they are finding for VRMS 2 is equals to what? And they are also telling you that T2 is equals to 525K. Well, now again, you see they are expressing a new RMS speed in terms of the old RMS speed. So you have to express the new in terms of the old. So you need to go back to your ratio comparison question technique again. First thing, what to express? So you want to express VRMS, so it will be VRMS 2 over VRMS 1. So that's our strategy. Second thing to do is you want to relate it to what? So as you know here, as you read in the question, the thing that you can relate to is the temperature, because the temperature is the only thing given. So it should be easy peasy. VRMS is just equals to 3 RT over the molar mass. So here, you think it's cool enough, we have our subject and we have things to relate it to. Okay, so we get this. I don't think there's need for any manipulation anymore. So now the third step is you want to compare VRMS2. Okay, the third step is algebra. So VRMS2 divided by VRMS1. VRMS1. So VRMS2, you can write it as 3RT over M. M should be capital M for molar. So this is situation 2 and divide by 3RT1 over molar mass 1. So if you do a bit of manipulation, it will be 3RT2 over M2 times M1 over 3RT1. So now here we need to plug in some relationship that we know. Well, we know 3R is constant, so we can just remove 3R. Then T2 and T1, you are given the value. So the only thing you have to know is whether the molar mass 1 is equal to the molar mass 2 or not. Well, the question is too short that they don't give you anything about it. So I think what you can do is you can assume them to be constant. Because most of the time our system, if they involve gas going out or coming in, only the the molar mass should be the same. Sorry. The molar mass should be the same because you never change your gas. If you change it from helium gas to oxygen gas, then probably the molar mass has changed. But they mention here, they mention nothing about changing a gas. So if they mention nothing about changing a gas, so M2 should be equals to M1. The molar mass should be the same because it's the same gas. There's no change. So if M2 is equals to M1, you can safely close out M2 and M1 as well. So what's left here in your equation is T2 over T1, which if you substitute in the value, 525 over 350, you get an answer of 1 over 5. Okay, you might get a value which is weird in your calculator, but if you do it slowly, you can actually see that this is 3, this is 2. So 3 over 2 is just 1 over 5. Okay, so once you reach this stage, I believe it's easy to see that VRMS2 is equals to square root of 1 over 5 VRMS1. VRMS1 is just equals to triangle bracket V. So once you reach that, we can safely pick our answer as square root of 1.5 triangle bracket V. So that will be our answer for question 15. So again, follow through the same 3 steps. I think you should be able to get your answer. So that's it for question 15. Do you have any other question left? Nope. So that's all for our chapter 13 revision quiz review. Thank you very much.